This lecture is part of the course Berkeley Math 115, which is an introductory undergraduate lecture on elementary number theory. So this lecture will be mostly about basic properties of divisibility, and we'll start discussing Euclid's algorithm. So first of all, we'll define some notation. We define a vertical line b to mean a divides b. You may think this means that b over a is defined. That's not quite correct. What it really means is that b is equal to x times a for some integer x. And if you think that's the same as saying b over a is defined, it's not quite, because 0 over 0 is not defined, but 0 is still x times 0 for any integer x. So in particular, we see that a divides 0 is always true for any a. 0 divides a is false unless a is equal to 0. Another example, 2 divides a is just a rather fancy way of saying that a is an even integer. So let's do something a little bit more interesting. We can show that 6 divides n times n plus 1 times n plus 2 for any integer n. So let's see why this is true. Well, if we look at this bit here, we see that n times n plus 1 is always even, because n is either even or odd, and if n is odd, then n plus 1 is even. So this is divisible by 2. And if we push this a little bit harder, we can see that one of these three numbers is divisible by 3, because if n must be of the form 3n or 3n plus 1 or 3n plus 2, and in any of these three cases, one of these three numbers is divisible by 3. This number here is always divisible by 2 and by 3, and since 2 and 3 are co-prime, this implies it's divisible by 6. Well, I haven't quite shown yet that if something's divisible by two co-prime numbers, it's divisible by their product, but that's something we will see fairly soon. It's kind of obvious in this case. Well, that's a kind of rather clumsy way of proving this number is divisible by 6, because we've had to break 6 up into 2 and 3 and then do a separate little tricky argument on both of them and then put them together. And there's actually a much neater way to show this is divisible by 6, which is to identify it with a binomial coefficient. More precisely, n times n plus 1 times n plus 2 divided by 6 is just equal to the binomial coefficient n plus 2, 3. So you remember what this number is. It's a number of ways to choose 3 elements from a 6-element set. And that's quite easy to see, because if we're choosing 3 elements, there are n plus 2 ways to choose the first one, and n plus 1 ways to choose the second, and n to choose the third. So there are n times n plus 1 times n plus 2 ways to choose the 3 elements in a particular order, but there are 6 different ways of ordering them, so we have to divide by 6. Now, the number of ways of choosing 3 elements from a 6-element set is obviously an integer, because we're just counting something, and that's going to give you an integer. So this number here is an integer, so 6 divides this number here. Another example, we always have 8 divides n squared minus n if n is an odd integer. So let's start just by checking a few cases of this. 1 squared minus 1 is 0, that's certainly divisible by 8. 3 squared minus 1 is 8, again, obvious. 5 squared minus 1 is 24, and so on. So we can check the first 3 cases. It's always a good idea in number theory to check the first few cases of a theorem, just to see what's going on and to make sure you haven't made some sort of stupid error. So now let's try and prove this is true for all odd n. Well, since n is odd, we can write m is equal to 2m plus 1 for some integer n. And now we find n squared minus 1 is 2n plus 1 squared minus 1, and we expand this out. It's 4n squared plus 4n plus 1, and then we've got to subtract 1 again, and this is equal to 4m squared plus n. And we're almost there, because we've shown this is divisible by 4, but that's not quite the same as showing it's divisible by 8, which is what we want to do. So to finish off, we want to show this bit here is even. And how do we do that? Well, that's kind of obvious. We just write this as 4 times n plus 1. And one of these two numbers must be even, because if n is not even, then n plus 1 is even. So this is 8m n plus 1 over 2, and this bit here is an integer. Next we just point out that the set of x such that d divides x is something called an ideal of the integers. So I'll just recall what an ideal is. Well, an ideal of the integers is just something that's closed under addition and subtraction. If you're working with general rings, the definition of ideal is a little bit more complicated, but for the integers we can get away with this simple definition. And that's kind of obvious because if two numbers x and y are divisible by d, then obviously their sum and their product is also divisible by d. So the set of multiples of any integer is always this ideal closed under addition and subtraction. Now we're going to discuss Euclid's division algorithm. This is not quite the same as Euclid's algorithm that we're going to discuss later. So Euclid's division algorithm says the following. Suppose that we're given a and b, which are positive integers. Then we can divide b by a with the remainder. So q is going to be a quotient, and r is called the remainder. And the key point is that we can take 0 less than or equal to r is less than a. In particular, r is in some sense smaller than the number a we're dividing by. And let's try and give Euclid's proof of this. Well, Euclid had a bit of a problem with division because the Greeks had no good notation for integers. I mean, the Hindu system of notation only turned up several centuries later, and before that came along, doing division was such a nightmare, it's not even clear the Greeks had a concept of dividing one integer by the other as an algorithm. What Euclid did instead was he represented integers, or numbers more generally, as line segments. So you might write b as a line segment like this, and you might have another line segment a. And then what Euclid did was he took the line segment b and you subtract a lot of copies of a from it. And you keep going until there's no room to subtract any more copies of it, and this little bit left over is then going to be the remainder r. And also notice that q is going to be the number of times you have to subtract a from it. Actually, Euclid had several other problems. First of all, he didn't really count 0 as a number at all, so he had to be careful to take b greater than a, otherwise you would have 0 copies of a, which is sort of not really, which kind of confused Greek mathematicians. Actually, they not only didn't count 0 as a number, they sometimes didn't even count 1 as a number, which makes this algorithm even more confusing. So this proves the algorithm whenever b and a are positive integers. In fact, you don't really need b and a to be positive if you don't mind not having to represent them by line segments. So instead we could take any a not equal to 0 and any integer b if you're willing to use negative numbers and 0. It's not too difficult to give the proof for negative numbers. Here we're subtracting copies of a from b because a and b are both positive. If b is negative, you'd have to add copies of a to b, and if a was negative, you'd again have to do subtraction instead of addition at some point. We can also notice that it's fairly clear that q and r are unique up to this condition here. I'm not going to prove that because it's very easy. We can also ask the following basic question. So I said, suppose we've got a number d, then the numbers x such that d divides x form an ideal closed under addition and subtraction. The converse is also true. If you've got an ideal, then I is equal to the set of multiples
And I think somebody asked, when did you first get interested in math? And here's the story he said. He said, well, when he was like 3, he was pick up some questions to pull out. So this is from the course website. As usual, remember that there is some homework to do, and we're going to do something. I'm actually going to change up the way that we're doing the homework a bit in response to a comment that came up in some other classes of it being hard to get to know other people who are in this course. I'm actually going to contribute. Just type raise hand into the chat. I see that there's someone already. Sarah Imani. Oh no, Sana. Is it Sana Imani?
Yeah,
Sana Imani.
so this is kind of like an idea that you use here is that any it's like because A, B, and C, if I'm not wrong, are integers, right?
Oh yes, they're integers.
Yeah.
Uh-huh.
So basically any like
closed under addition and subtraction. The converse is also true. If you've got an ideal, then I is equal to the set of multiples of some number d greater than or equal to 0. And the proof of this makes use of Euclid's division algorithm. What we do is we suppose I has some element a greater than 0. If not, I is just equal to a single element 0, and the result is easy. I is just the set of multiples of 0. So we may as well assume that it's got some a greater than 0. And we pick the smallest a in I with a greater than 0. And there must be a smallest integer, because if you've got any non-empty set of positive integers, it must have a smallest element. Now suppose b is in I. What we do now is we write b is equal to a times q plus r, with naught less than r is less than a. And now we notice that r, which is equal to b minus aq, is also in I, because I is closed under addition and subtraction. We can get this from a and b by subtraction. So because a is the smallest positive element, this implies that r must actually be equal to 0. So b is equal to a times q is a multiple of a. So I is just the multiples of a, where a is the smallest positive element in I, unless I is non-zero. So this is a basic application of Euclid's algorithm. It shows that ideals of the integers are exactly the same as multiples of some particular
This is the first in a series of videos that I'm making to support a number theory course that I'm teaching this semester. And here we're just going to lay down the basic framework to move on to more standard number theory results like divisibility. Modular arithmetic, quadratic residues, primitive roots, and all of the stuff like that, which we will cover in this course. So I want to start off with our most basic object of study in this course, and that would be the natural numbers. So we will not completely construct these natural numbers in a set theoretic way, but we will prove some things involving the Peano axioms a little bit later. So let's just recall that by the natural numbers, we mean the positive integers. So we've got 1, 2, 3, 4, 5, so on and so forth. We will not consider 0 a natural number in this course. So there are two standard operations on the natural numbers, addition and multiplication. So addition is commutative, it's associative, multiplication is commutative and associative. And furthermore, we've got this nice distributive rule of multiplication over addition. Also, the natural numbers are something called a well-ordered set. And that means that if you've got two non-equal elements, you can always decide which one is larger. So I've written that here. So if you've got m and n, which are natural numbers, and they are non-equal, then we know m is less than n or m is greater than n. You might take this for granted, but there are sets which are not well ordered. They are partially ordered, or even worse, not ordered at all. For example, the set of subsets of a set is partially ordered. Sometimes you can compare them via inclusion, but sometimes you can't. Okay, another couple of things that we'll take as fact are the Archimedean principle. So that says if we have a non-empty set of natural numbers, it must have a least element. Also, as needed, we'll use the principle of mathematical induction. We'll have a whole video devoted to kind of practicing mathematical induction a couple of videos from now, but let's just recall kind of its basic set setup. If we've got a set S of natural numbers satisfying two conditions, so 1 is an element of S, and if k is an element from S, that implies that k plus 1 is an element from S. Then S is in fact the whole natural numbers. So you can think about 1 being in S as being our base case. Then k being in S is like our induction hypothesis, which implies the induction step, k plus 1 is in S. And then S being all natural numbers would be something like a formula holding for all natural numbers. So we're also going to study the following sets, which are extensions of natural numbers. So the integers. So that's all positive and negative natural numbers, and then 0. So I wrote it like this: 0 plus minus 1 plus minus 2 plus minus 3, so on and so forth. We'll also look at rational numbers. So that'll be all ratios of integers where the denominator is not 0. So we've got like a half, a third, minus 99 over 54,000. You know, there are lots of examples of rational numbers. Okay, so now that we've got these well-known objects and facts out of the way, let's jump into our main goal of this first video, which is to look at the Peano axioms and show that addition and multiplication in the natural numbers satisfies these axioms. So now that we've looked at the natural numbers, we want to look at a more formal approach to the natural numbers called the Peano axioms. So the Peano axioms for the natural numbers are as follows. So let's see, we've got 5 of them over there. So it says that 1 is a natural number. If n is a natural number, then n plus 1 is a natural number. So in other words, everything in the natural numbers has something called a successor in the natural numbers, which we're calling n plus 1. Then if m and n are natural numbers such that m plus 1 is equal to n plus 1, in other words, the successor of m is equal to the successor of n, is an injective or a one-to-one function. Next, there is not a natural number n such that n plus 1 is equal to n. And then finally, we've got this inductive action on the natural numbers. And so that really reads just like the induction that we had before. So if S is a subset of n containing 1, and if n is an S, that implies n plus 1 is in S, then that means S is equal to natural numbers. Okay, and so we can actually define these axioms. So we want to start with if n sub there is not a natural number n such that n plus 1 is equal to n. And then finally, we've got this inductive action on the natural numbers. And so that really reads just like the induction that we had before. So if S is a subset of n containing 1, and if n is an S, that implies n plus 1 is in S, then that means S is equal to natural numbers. Okay, and so we can actually define addition and multiplication via these axioms. So we want to start with a successor function. So that's going to be a function s from n to n, and we'll just notate it like this: s of n equals n plus 1. So I want to reiterate that we don't know how to add natural numbers yet. We don't know how to multiply natural numbers yet. But what we do know how to do is get to the next natural number. And we do that via the successor function. So we can't do something like 5 plus 4. That's impossible so far. But we can find the number that's after 5. That's obviously 6. But if we can find the next number, we can actually define addition and multiplication recursively. And that's exactly what we'll do right here. So we can define addition as follows. So like I said, the successor of n is n plus 1. And then we can recursively define m plus the successor of n as the successor of m plus n. So let's see how that works and how that really gives us a recursive definition of addition on the natural numbers. Let's say 5 and 3. Now we can apply this formula that we're baking into the definition of addition to say that this is going to be the successor of 5 plus 3, but that's the successor of 8, because now we know how to add 5 and 3, because that's happening like lower down in the induction than 5 plus 4. So we've assumed that we've recursively defined everything up to this 5 plus 4, not including the 5 plus 4, so we know how to do 5 plus 3. I know this is like kind of abstract and sticky. But this is actually a really important take on the natural number arithmetic. Okay, but what's the successor of 8? That's obviously equal to 9. So 5 plus 4 is 9, so we're good to go there. Now let's look at multiplication. So a priori, we don't know how to multiply two natural numbers, like for example, 3 and 6. But we can define multiplication via the successor function recursively again. So we'll define it so that 1 is the multiplicative identity. So that makes sense. We've got n times 1 is equal to n. And then m times the successor of n is equal to m times n plus m. And I want to point out that if we write the successor of n as n plus 1, let's notice